I'm going to explain the structural analysis of a beam using ANSYS mechanical APDL. So ANSYS has two elements defined. One is beam 188, another one is beam 189. So beam 188 has the two nodes at the end, which is a linear element. Another one is the beam 189, which has the node at the midpoint also, which is the quadratic. So here I have shown the difference between linear and quadratic. So only at the end point there is a nodes. In the quadratic there is a point in the mid also, mid portion also. Because of that, what happens? You see the top one is the exact solution. So this is the exact solution. So if you use the coarse mesh of the linear element, you can see this much is the mismatching. Instead, if you use the coarse mesh of the quadratic, you can see how much it is aligned with the exact one. So if you want to match with the exact solution, then you should have the quadratic type, or just a simple understanding or basic study, you can go for the linear one. And in the ANSYS Fluent, we have in the post processing we have options for vector plot, that is contour, XY plot, etc. and all. Similarly here, to get that output contour, they have given the element table I and j value. Depends upon that moment and shear force bending moment diagram, we have to call these numbers ij numbers. For example, here they mention. So if you want to find the shear force along the z direction, then you have to enter this number 5 and 18. And if you want to find the moment about y direction, then you have to call this 2 and 15, like that. From these numbers only you can get the results. And here just I explain different types of beam endpoints. First one is the fixed. Fixed means there is no translation, there is no rotation. Then roller support. So roller support, so other than this vertical direction, other direction it can translate, also it can rotate. Then pinned one. So in the pinned one, so there is no translate, only it can rotate, like that. Different types already I have studied. So I am going to take first one simply supported beam, one side pinned one, so that this direction only it will rotate. Another side roller support, so that it can translate, also there will be a rotation, like that. This kind of simply supported beam first I am going to analyze. And here I have shown just shear force and bending moment diagram for different simply supported, cantilever, etc. and all. So first one is a simply supported with a pointer in the midpoint. This is how shear force and bending moment will vary. Then this is the same point load but little offset from the midpoint. Then this is the uniform distributed load for the simply supported. This is how shear force and bending moment varies. Then the same simply supported, again same UDF, which is throughout the length. Then this is the uniformly varying load where maximum is at the center. Then this is uniformly varying load, like that. Three different distributed load, how shear force diagram and bending moment diagram varied, they have shown. Then cantilever beam, again one end is fixed and one end we are applying the point load. Here uniformly distributed load, here UDF and UDL, also the concentrated load, both they applied. For that, how shear force diagram and bending moment diagram varied, they have shown. Same, this is cantilever, and they applied the UDL only for the one portion from the free end. And here the next one is the UDL, which is varying from the fixed end, and this is the uniformly varying load from the free end, like that. Different load configuration they have shown. And this for the fixed one, point load and uniformly distributed load. So I will show just 2-3 cases. You can try the remaining cases. So just the first problem, you can take some arbitrary value also. They have mentioned 2.2 meter span, load is 22,840 Newton, and they have given the I section, or you can take rectangular section, any section you can take it. And for the steel they have taken 2 in 10 power 7 Newton per centimeter square. Newton per meter square, if you change it will be 10 power 11, then Poisson ratio 0.27. With that you will go for the just a simulation. So you have to open this mechanical APDL. So two window will be opening. One is this command window, another one is this main window. So first step, I am going to change the unit system. So further just slash unit comma SI, caps or small letter, anything will work. If you enter here, you can see everything is taken as a SI unit. So unit is changed to SI. Next you have to change it to on which directory you want to change and what is the job name, file name. For example, I am saving this in desktop and job name maybe just simply supported beam. Then here also, like other ANSYS etc., there will be a pre-processor, then solution, then there will be a post-processor, like that same setup will be there. First preference. So using this you can do structural, thermal, magnetic, all the analysis. So I am going to do the structural analysis. Then the pre-processor, first the element type you have to define. So add, another one add. So we are going to define do the analysis for beam. So two types of beams are there, linear and quadratic. So I am taking this linear 188. Okay, close. So element is defined. Then what is the material I am going to use? So in that material model, so structural, linear, elastic material, isotropic, and if it is steel, that will be 2 e power 11 Newton per meter square and Poisson ratio 0.27. So material I have defined. So element I defined, material I defined, then section, what type of section you want to take. So this is the beam, and first I will try this rectangular. In another video I have tried the I beam, that also you can see. So I am just taking 0.12 meter. Preview you can see how it varies. So cross section also I defined. So element I defined, material defined, cross section I defined. Now modeling. So I am going to create the beam length. So first we have to create the point. Using that I am going to create the line. So first point using coordinate system. So I am going to take 3 points, that is 2 fixed end, that is 2 end and center point to apply the load. Okay, so I am going to simulate maybe this, maybe the first case I will take it, simply supported beam, 2 end supports and 1 center point for applying the load I will take. 0. Second point is at 1.1 meter midpoint. Then third point, another end 2.2 meter, like that I have taken. So all points are now created, 1, 2, 3. Then I can draw the line. So I'm going to draw a straight line from here to here, one line, then from here to here another line. So we have created the line. Then meshing. So first I'm going to define the element size. So manual size, global size, just I am taking divisions. For example, minimum I will take just some 50 divisions. Okay. Then mesh tool, I have to select mesh, then select these two lines. Okay. So meshing is done. So now pre-processor is done. Then we have to go for the loading. So open the load, define the load by applying it. So we are going to do the structural analysis. Structurally, first you have to display, we have to fix the displacement. So I said this will be the pinned end and this will be the roller support. So first in the key point we have to define the displacement. First this point I am picking it. So if it is the pinned end, there is no translation, and rotation also, or it will be rotating only about this z axis. About the z axis alone it will rotate. So other things and all we have to constrain. Okay, so pinned end means it can rotate only about the z axis. Apply. Then next line, next point, this will be the roller support. That means along the x direction it can translate. Okay, also about this axis it can rotate, like that it will vary. So here all there is no translation at all. If it is roller along this direction alone, there will be a translation. That is the difference between pinned and roller. Okay, both side it can rotate, but in the pinned support there is no translation. In the roller support there can be a translation only, that is a different. So displacement you defined, then force. See, for the point load you will use this force option. Otherwise, if you want to apply the UDL, you can go for this pressure also. So first point load case I will take it. So at the key point in the center, along this y direction, maybe value I mentioned 22840 Newton I mentioned. So acting downwards I put minus. So I applied all the loads. Then we can solve it. So solve current load setup. Okay. Solution is done. We have taken just 50 iterations, so it is easily done. Then we can go for the post processing. Here only I mentioned, so to see the results, shear force, bending moment area, etc. and all, we are going to use the element table. So here is the element table and define table. So here only we are going to define those numbers. So add. So there's a sequence numbers given. So in the table, if you see, so we have applied the load in the y direction. So shear force in the y direction, if you want to find, it should be 6 and 19 to find the shear force. Okay, SMIC 6 and 19. So add sequence number, first 6 you load. So in the newer version, we are getting some warning error. Okay, so if the window is hidden, you can use this raise hidden button. So you close first this one, then close, then close. So to avoid that error, you have to do this command set comma last to reset to retrieve the results. Set comma last. Now you try define table, load sequence number 6 and 19. I think 6 and 19 is for the y direction shear force. 6 you apply, then 19 you apply. Then to see the moment about this z axis, it should be 3 and 16. So 3 and 16, like that. I have loaded the element table sequence numbers to get the results. So once you define the table, you can go for the plot results. You will see the contour, how it varies using the line element sequence numbers. So it was mentioned 6 and 19. So 6 and 19 you load, you can get the shear force diagram for the simply supported beam. Then for the moment, it should be 3 and 16. You apply, you can see the bending moment diagram. So this is for the simply supported beam. Then we will see cantilever beam also next. And additionally, you see the nodal solution also. We can see the displacement vector. And you can see the one misses stress, that value, etc. You can see. Even you can visualize this as a 3D. So you have to go to this plot control, style, size and shape, display of element you on, then OK. Now you can see this as the 3D element. You can see the isometric view also. So nodal solution, just a displacement vector, how it varied, then stress, how it varied, you can see in the isometric view also. Even you can save this as the video. For that you have to go to this plot control, animate, either only the deformed shape you want to see or the result you have to see. For example, result you go. If it is hidden, you can use this raise hidden. So displacement, OK. You can see the animation forward, backward, or only forward. Like that isometric view also you can see. Okay, now we go for the cantilever beam. That is, this case is simulated simply supported beam with a pointer in the center. Next we will go for this cantilever. One end is fixed, another one is free, where we are applying the load. We will get this kind of shear force and bending moment diagram. We will see this. So first I am saving this file. So save everything. Now open once again. So mechanical APDL. So two windows, command window and this one. Same procedure. I will set the unit first. You can check either it is loaded properly or not. Unit is set to SI. Then directory is desktop and the file name is cantilever beam. Then preference, structural analysis, then the solution, first element type, so beam 188, then material models, structural, linear, elastic, isotropic and 2e power 11 for the steel, and here 27 which was given in the problem, same thing I am taking. So material is defined, then section, same, just a rectangular square section, 0.1, preview, okay. So section, cross section is defined, then the line we have to draw. So first key point, here 2 point is sufficient as it is cantilever. One is 0, 0, then second point is straight away 2.2 will go, 2.2. Then line as a straight line from here to here, okay. Once modeling is done, I can go for the meshing. First size control, manual sizing, global sizing, just distance 50, and then we can mesh it using mesh tool. So mesh, select the line, okay. So meshing is done. Then load, so define the load by applying it. Structural load, first displacement, so one end is fixed, so displacement on this key point, so one end is fixed means, so all degree of freedom will be arrested, or you leave that, you select everything, anything you can do. So this is a fixed point now, and one end is free, so in order to define anything, then force again on this key point, free end, I am applying the load in the y direction, minus maybe same thing, 22840 Newton. So load also applied, displacement also fixed, and then we can solve current load setup, okay. Then post processing, again first you are defining the element table to get the shear force and bending moment. The number is 619, 316. This time also error will come, I think. 6. Okay, you have to cancel, close. You have to do set comma last. Now you try. Add. Sequence number is 6, 19, 3, 16. Okay. Now we can plot the results. We can go for the contour plot, line element results. So 619 you apply. So this is the bending moment diagram, shear force diagram for the cantilever beam. Next you go for the bending moment diagram. Same line element result. This time 3 and 60. Apply. So this is the bending moment diagram. Okay, same thing we got it. Here also you can see that isometric view, size and shape. Okay, enable. Then if you want, you can animate deformed results. First deformation. Okay, you can change the view. So stop, close, change to isometric view. It will be easy to visualize. So animate deformed result, deformation. So this is how deformation happened. And to save the files, so there is an image caption. So capture to file, quality can be the presentation, color, landscape, and you can save it as a JPEG or PNG like that. All those shear force diagram, bending moment diagram, everything you can save it. So this is for the simply supported on cantilever. So for the cantilever beam, if it is a point load at the free end, this is the shear force diagram and this is the bending moment diagram, the first one. For the same cantilever beam, if you apply a uniformly distributed load, then shear force bending moment diagram will vary. Mainly the shear force diagram, you can see the major difference. Here it is like a rectangle, here it is like a triangle. Same thing you will try. Only one difference, same node conditions, that is all degree of freedom is arrested here and this is the free end. Previously you uploaded one point load in one node at the end. This time, that is, we use the force option. This time we are going to use the pressure option. Okay, pressure on this beam, that option alone we are going to change. Remaining all the procedure is same. So I am just skipping the further procedures because same thing, how to define the element, material, cross section, mesh generation, everything is same. And defining the load alone while applying. So displacement is same only, that is all degree of freedom here, this is the free end. Then instead of applying the force, you have to apply this pressure. Okay, in the pressure you can see the last option, beam. Select the beam. You have to pick all because already we have divided into small sections. So you have to do pick all. Okay, so pick all. Here you can change the numbers. If it is 1, Z direction. If it is Y direction, means 2, like that you have to change it. So I have to apply load in the Y direction. So the load key I am changing to 2 from 1. Then what is the pressure value you have to enter here, Newton per meter square. Just randomly I have taken some 10,000 Newton per meter square. And if it is uniformly distributed load, you have to leave the second one as the blank. It will be taken for the throughout the length. Okay, if it is uniformly distributing load. So here you have to go to the pressure. You have to select on beam, pick all. Okay, not single beam, not single section. You have to pick all the elements along this beam. Then at which direction you want to apply the load. Y direction means 2, Z means 1, like that. Then what is the pressure value? You enter. Remaining procedure, everything is same only. You have to solve. Then general processing. Then element table you have to define. Then plot result, contour, line. So 6 and 13 is the 3 and 16 is the, so 3 and 16 is the moment diagram, 6 and 19 is the shear force. Okay, 3 and 19 is the moment diagram. See, we are getting this like a gradient moment diagram, same thing as this. Then shear force diagram, we will see shear force diagram 6 and 19. You apply. Now this is the shear force diagram 6 and 19. Okay, same as mentioned in the example. Okay, like that you can vary the point load, uniform distributed load, cantilever, simply supported. In any case you can try. Yeah, that's it.